Alright guys. Cool. Okay, so let's see. Yeah, you can see everything. In class today, we figured out how you find the kinetic energy of an electron that gets ejected from the nucleus of a hydrogen atom. And we're basically going to do the same thing and then expand it to include what we did in the first part of class, which is basically find the potential energy between, in this case, an electron and a positively charged plate. And so the things that you need to know are all listed here. And so every equation and constant and conversion factor should be up there. So the practice problem is going to be with the electron in a hydrogen atom at the n equals 2 level, so n equals 2 shell, gets hit by a photon of 200 nanometers, wavelength of 200 nanometers, and is then accelerated towards a plate that is creating a voltage gradient between the electron and the plate of negative 10.8 volts. And it's negative, this is important to understand that it's negative because the potential energy when it hits the plate is 0, and the potential energy when it's as far away as when it gets ejected from this hydrogen atom is greatest. So the initial is greater than the final, therefore you have a negative voltage. Okay, so that's important for getting the right sign for this problem. So the first thing that we need to do is something that we already did in a problem today, and that's find the kinetic energy of the ejected electron. So all you have to do that is take the energy of the photon that it's absorbing and then add that to the energy of the electron in its orbital. And so what you end up finding for the energy of the photon is 6.2 electron volts, and you get that by doing Hc divided by lambda. So Hc just equals 1240 nanometers times electron volts. Divide that by 200 nanometers, and you end up with 6.2 electron volts. And then, since it is in the n equals 2 subshell, to find the total energy of this electron, you just take negative 13.6 electron volts, because this is an electron, and then divide that by n squared. So 13.6 divided by 4 gives you negative 3.4. So the kinetic energy of this electron as it's ejected is just 6.2, the energy it absorbs, minus 3.4, which is the energy basically holding it in. And that gives you 2.8 electron volts. I think we literally did that exact problem in class. Now what we're adding is something that we kind of did at the beginning of class, where you find the potential energy. And he kind of gave us the equation for potential energy with this being like K times Q divided by R, and then times Q test. But you don't have to worry about that because we already gave you delta V, which is basically everything other than that Q test. The Q test is in fact the charge of the electron, because that is the test charge in this case. So basically we're just adding this kinetic energy that we got from ejecting the electron, and then adding the potential energy it starts with from this plate that we have, that this plate is creating, because by the time it hits that plate, all of that potential energy will turn into kinetic energy. So the kinetic energy when it's striking the plate will be the kinetic energy it started with by ejecting it, plus the potential energy that it had once it was ejected that was caused by this plate. So to find that potential energy, you just take the charge of the electron, which is negative 1.6 times 10 to the negative 19th joules, and multiply that by the voltage, which is negative 10.8 volts.
And then we all have to divide that.
Yeah, and so that's going to give you an energy in joules. And that's not what we want. We want an electron volt, so it's the same as the other thing. And so we just use that conversion factor, which is 1.6 times 10 to the negative 19 joules per electron volt. So basically, you're just taking this voltage and flipping the sign, because we're taking negative 1.6 times 10 to the negative 19th and dividing it by positive 1.6 times 10 to the negative 19th, meaning you're just adding 2.8 plus 10.8, which equals 13.6. So I need to at least turn this over so everyone can see that in the video. And so that's how you do this type of problem if you have an electron that is ejected and then accelerate toward the plate immediately following that. Does everybody understand?
Did you say you're adding potential energy?
Yeah, so this is kinetic energy, and then this is potential energy. So this is the kinetic energy when it leaves the hydrogen atom. This is the potential energy when it leaves the hydrogen atom.
How do you find potential energy, like variable-wise?
So potential energy equals Q times delta V.
Oh.
Yeah. And so that's shown here. And then that delta V, he said you could find another way. Basically, is equal to K Q times Q over R.
Okay.
Yeah.
Got it.
That's that equation for potential energy. Okay.
Cool.
Cool. So that's all we're doing.